We will further study dynamic NMR, temperature dependent NMR, NMR of fluxional molecules. In the case of ethane, there are two methyl groups. The two methyl protons, the six methyl protons are equivalent because of CC single bond rotation. They are very fast on NMR time scale compared to NMR time scale. Therefore, it appears as a singlet. In this, we will study the conformational exchange process in cyclohexane molecule. There are two types of protons in cyclohexane: axial proton, equatorial protons. Due to ring flipping process, axial proton become equatorial and equatorial proton becomes axial. Therefore, at room temperature, two signals are expected due to axial and equatorial protons, but at room temperature, only one singlet signal is observed, single average resonance is observed, whereas on lowering the temperature, on lowering the at for example at high temperature, a single average resonance is observed due to fast exchange ring flipping process. The interconversion of axial to equatorial, equatorial to axial due to ring flipping is so fast by on decreasing the temperature, the two signals are resolved now. In this, let us see the effect of temperature and magnetic field on the NMR spectra of fluxional molecules. With the increasing temperature, there is a fast exchange and the two signals slowly merge and become single sharp line. With the increasing field strength, the the two signals are well resolved. Here, how NMR is used to study hindered rotation in N prime dimethyl formamide. In N dimethyl formamide, there are two methyl groups. These two are at low temperature. The two protons are chemically distinct. Therefore, they will give two signals as it is shown here. As you increase the temperature, the two signals just merge at the just merge at that time. Tau equal to the residence lifetime, the lifetime of methyl proton A in this state, square root of 2 pi nu A minus nu B, where nu A and nu B are the resonance frequencies of the two methyl protons. Using the temperature dependent NMR, we can calculate the rotational rate constant for this hindered rotation process. We know that 1 by tau lifetime is equal to the rate constant. Therefore, the rate constant for this rotational exchange process can be calculated using dynamic NMR. Here, we will study what are fluxional NMR fluxional molecules. These fluxional molecules are molecules that undergo dynamics, constantly exchanging their positions. For example, PF5, SF4, these are all trigonal bipyramidal geometries. They have trigonal bipyramidal geometries. They undergo very pseudo rotation. That is, it occurs via square pyramidal geometry. The axial, due to this rotation, axial positions become equatorial, equatorial becomes axial, as you see here. The DPP and square pedal geometries, the energy differences are very little. Therefore, they undergo very pseudo rotation to give a fluxional character. For example, BF5 fluorine 19 NMR is used to study the very pseudo rotation. In this case, carbon 13 NMR is used to study the fluxional character of this molecule. Fluorine 19 NMR is again used here. The structure of SF4 is obtained from the NMR. For example, at room temperature, single peak is observed. For example, because of constant exchange of axial and equatorial position, they are equivalent. They are equivalent. All the fluorine atoms are equivalent. On lowering the temperature, it splits into two signals. First, it splits into two signals due to axial fluorine and equatorial fluorine are chemically distinct. Further, on lowering temperature, each fluorine, each peak is split into triplet. For example, the axial fluorine are split into triplet because of this coupling with these equatorial two fluorine atoms. Each peak is split into triplet. Let us see here the NMR spectra of ethanol. The structure of ethanol is shown here. The high resolution NMR spectrum of pure ethanol is given here. The methyl protons couples with the methylene proton to give triplet n plus 1. By following the n plus 1 rule, it gives triplet. Similarly, methylene proton couples first with the methyl protons to give tetrat, and it further splits into doublet due to coupling interaction with the OH proton. And the OH proton on coupling with the methylene protons to give triplet n plus 1, 2 plus 1 triplet signal. Whereas in the presence of acid, when you add acid to ethanol, the proton, the OH proton undergoes continuous exchange with the acid proton. As a result, it becomes a singlet. It becomes a singlet, and the methylene protons do not couple with the OH proton. Here we will study about nuclear double resonance NMR technique. In double resonance NMR technique, it uses two different radio frequency pulses called double irradiation or spin decoupling technique. It is very useful and advanced NMR technique for simplification and interpretation of complex NMR spectra of complicated molecules, protein molecules, etc. For example, in this, I have shown the NMR spectrum of pure ethanol. When methyl proton is irradiated, it collapses and the signal disappears, and also CH3 proton does not couple with the methylene protons. Therefore, methylene proton couples only with the OH proton to give doublet. In this, we will study about what is nuclear Overhauser effect, what is NOE. For example, this is a protein molecule or organic molecule where there are three protons, A, B, C. So there are three different protons, they give three different chemical shift, and A and B are spatially closer together, whereas C is not closer together. When using double resonance technique, when A is irradiated, when A proton is irradiated, there is a change in the intensity of the NMR peak of the B, because A and B are close to each other. The signal increases. If the signal increases, amplitude increases, it is called positive nuclear overgaser effect. If the signal of the B proton decreases, then it is called negative nuclear overgaser effect. In other words, there is a change in the intensity of the nucleus B when the nuclear spin states is perturbed. This phenomenon is known as nuclear overgaser effect. This effect is very, very important because NOC spectroscopy, 2D NMR spectroscopy are based on nuclear overgaser effect. And it is very useful for the three-dimensional structure determination of organic compounds, including proteins, the DNA, etc. For this effect, Overhauser was awarded Nobel Prize. NOE effect occurs through space as due to dipole-dipole interaction relaxation. Its magnitude is inversely proportional to the sixth power of the distance between the two interacting nuclei. For example, A and B in this case. It is useful for the studying the three-dimensional structure and stereochemistry of organic compounds. Here, let us study the effect of chirality on NMR. Most of the amino acids are chiral molecules. They have asymmetric carbon atom in it. For instance, cysteine is an amino acid. If you look at the 2D structure, the methylene protons are equivalent or identical or expected to be equivalent. The methylene carbon atom is prochiral. If you look at the 3D structure, the methylene protons are not chemically identical. They are chemically distinct and therefore resonate at different chemical ship values, as you see here. And for example, Hp proton couples with the Hc proton because they are not chemically equivalent. They are also not magnetically equivalent. And further, it couples with the A proton to give tetrate. Let us see quickly a few applications of NMR to inorganic molecules or inorganic compounds. One, metal hydrogen bonding in this complex molecule is established using proton NMR. The nuclear quantum number of rhodium nucleus is 1 by 2. Therefore, proton NMR gives a doublet because of the direct bond coupling gives a doublet. This establishes a bond between rhodium and hydrogen. The structure of phosphorus acid is elucidated by using phosphorus NMR. The formula of phosphorus acid is H3PO3. There are two possible structures I have given here. In this case, phosphorus 15, I'm sorry, this is phosphorus 15, I equal to 1 by 2. And phosphorus NMR, using phosphorus NMR, this compound will give you a doublet, whereas this compound will give you a triplet. The OH protons does not couple because of fast exchange with the water molecules in the solvent. In actually, triplet signal is obtained. Therefore, the correct structure is this one. Similarly, the structure of fluoroderivative is also obtained. What is the structure of PF6 minus? It is established, elucidated using phosphorus 31 NMR. Sorry, previously I told 15 phosphorus 31 NMR mass number. It gives a septed signal, 7 lines. It reveals that that is fluorine phosphorus NMR. There are 6 fluorine atoms. Therefore, phosphorus couples with the 6 fluorine atoms to give separated signal, 7 lines. It reveals that all the fluorine equivalent. Therefore, the geometry is regular octahedral. pH 4 plus, like NH4 plus ammonium ion, phosphonium ion, using phosphorus 31 NMR, it gives a phosphorus 31 couples with the 4 proton to give quintet 5 lines, n plus 1 with intensity ratio. Whereas proton NMR, all the protons are equivalent. It couples with the phosphorus 1, I equal to 1 by 2. Similarly, BRF5, the structure is studied by using fluorine 19 NMR. In this case, there are 2 peaks were observed with intensity ratio 4:1. It shows that there are 2 kinds of fluorine. 4 are one type and 1 is a different type. The intense line is doublet. The intense line is doublet because it is tetragonal pyramidal. Then the four equatorial fluorine atoms couple with this proton to give intense signal because of 4 fluorine atoms is doublet. Weak line, this is only 1 fluorine atom couples with the 4, therefore n plus 1 pinned at 5 lines. Therefore, the structure is symmetrical tetragonal pyramid from NMR studies. NMR is also used to investigate the cis trans isomers. For example, in platinum complex, the cis isomer will have different coupling. Platinum I equal to 1 by 2, phosphorus I equal to 1 by 2, coupling constant. It is cis 3.62. From the coupling constant values, the cis trans isomers can be determined. In fluorine 19 NMR, the structure of dimethyl phosphorus trifluoride structure is elucidated. At low temperature, 2 peaks are observed. At room temperature, due to perirotation, fast exchange, only 1 peak is observed. That are all are equivalent. 1 fluorine in axial position and 2 in equatorial position. Using NMR, this structure is up. Here we will study what is magic angle spinning. Only it is important in solid state NMR. In solid state, the compound gives broad line in NMR spectrum because of increased line width due to spin lattice relaxation, due to fast spin lattice relaxation, due to dipolar chemical shift anisotropy. These effects are averaged out in solution when the compound is dissolved in solution. These effects are negligible. These effects are negligible. They will give isotropic NMR spectrum because due to rapid tumbling motion. However, in solid state, these effects are very significant. The sample is rotated about this axis, makes an angle with the external applied magnetic field, theta equal to 54.74 degree. The dipolar chemical shift anisotropy is directly proportional to 1 minus 3 cos squared theta. When theta equal to 54.74, these two effects become zero. Therefore, the lines are narrowed with the lower line width or time. The spectrum is well resolved at this magic angle spinning of the sample. We'll quickly see the EPR spectroscopy. In the absence of magnetic field, the two spin states are degenerate. In the presence of external applied field, the two states splits. The energy of separation is given by, we have seen earlier, G, E, beta, B naught. That beta is the Bohr magneton, G is the E value, B naught is the applied field strength, H nu, the resonance condition is H nu equal to Ge beta B naught. The electron spins about its own axis and also rotates, revolves in an orbit. As a result of this, there will be, I forgot to tell, ESR spectroscopy is also called electron spin resonance spectroscopy or electron paramagnetic spectroscopy, resonance spectroscopy, or electromagnetic resonance EMR spectroscopy. How the EPR spectra are presented? Because of this transition between the two electron spin states, there will be an absorption signal. The absorption signal, as you see, it is not well resolved. There are so many peaks, it is buried. So the derivative signal in EPR, the signal is always presented in first derivative. When you take the first derivative of this absorption signal, the hyperfine splitting signals are well resolved. What are absorption and derivative EPR spectra? Why derivative EPR spectra are important? EPR is a very sensitive technique than NMR. However, due to short relaxation time, we have seen earlier, as in paramagnetic system, the absorption signals are always broad and hyperfine structures we have seen earlier in the slide. Hyperfine structures are buried. Therefore, derivative signals are obtained using phase sensitive detection technique to get well resolved hyperfine features. Here I have shown the schematic diagram of EPR spectrometer. It consists of electromagnet similar to NMR, sample holder, and amplifier and detector. In this case, we will use microwave bridge. It is used to generate the microwave, monochromatic microwave. For expand, it is 9.8 gigahertz. For expand, it is 9.8 gigahertz. It will produce Dunn diode. Is used to generate the monochromatic microwave radiation. It uses phase sensitive detector to convert the absorption signal into derivative signal. It is the actual EPR spectrometer. These are electromagnets. This microwave bridge, microwave guide, and you have temperature controller, liquid helium to measure low temperature EPR. Similar to spin-spin coupling constant in NMR, in ESR we have hyperfine coupling interaction, hyperfine splitting. It is represented by A, whereas in NMR it is represented by G. It occurs due to the coupling between the spin magnetic moment and the nuclear magnetic moment. We will see further. The spin Hamiltonian for the EPR is H cap equal to H cap E electron zeeman plus hyperfine coupling interaction. Hamiltonian corresponding to hyperfine interaction. The energy of this Hamiltonian is given by this. We have studied this in G mu B B ms, where ms is the quantum number plus or minus half, and hyperfine coupling term. A is the hyperfine coupling constant. Ms is the spin magnetic quantum number, nuclear magnetic quantum number Mi. For liquids and gaseous samples, The hyperfine coupling interaction or isotropic because of constant tumbling motion. The anisotropic effects are averaged out as we see in magic angle spinning. For solids, there will be anisotropic. The hyperfine coupling is anisotropic at different angle. You measure, will give different value because of anisotropic character. ESR signal further splits into several lines because of this hyperfine splitting as in spin-spin coupling. What are the important characteristics of hyperfine coupling? As the spin-spin coupling, it is similar to spin-spin coupling. It depends on the magnitude of nuclear and electron spin magnetic moments. Electron spin density near the nucleus because electron spin couples with the nucleus called a thermic contact term. Similar to J value, A value is independent of applied magnetic field, and n plus 1, it obeys n plus 1 rule. If I equal to 1, then 2ni plus 1, it is similar to spin-spin coupling. The intensity ratio is given by Pascal triangle. In NMR, chemical shift value, similar to chemical shift value in ESR, G value is obtained. For free radicals, organic free radicals, there will be no spin orbit coupling. What is spin orbit coupling? What is spin orbit interaction? As I said earlier, the electron spins about its own axis and also it revolves in orbit. Therefore, it is having the electron is having spin magnetic moment as well as orbital magnetic moment, orbit magnetic moment. These two magnetic moments coupled to give spin orbit coupling, depending on their relative orientation. For free radicals, this spin orbit coupling interaction is negligible. Therefore, the GE value is close to free electron value 2.0023. However, for transition metal complexes, the G values are very much different from the free electron value due to this spin orbit coupling. Let us see an example to illustrate this hyperfine coupling. For example, hydrogen atom. In the hydrogen atom, you have one electron with the spin s equal to 1 by 2 and proton I equal to 1 by 2. In the absence of magnetic field, the electron spin states are degenerate. In the presence of magnetic field, it splits into two, we have seen earlier. And further, the two spin states, each spin state is split into two levels due to coupling between the electron spin moment and nuclear spin magnetic moment. Therefore, it splits into two. In the case of ESR, minus 1 by 2 is the lowest energy state, whereas in the case of NMR, plus 1 by 2 is the ground state. Therefore, by following the selection rule, delta Mi equal to plus or minus 1, there are two transitions. Therefore, there are two signals. There are two signals obtained due to hyperfine splitting due to I equal to 1 by 2. The hyperfine splitting constant is calculated from the spectra as shown here. Let us see few more examples. Cyclopentadienyl. Here it is a free radical. It's a paramagnetic molecule. The electron is delocalized. The unpaired electron is delocalized over 5 protons. Therefore, n plus 1 rule. Therefore, sextet, there are 6 lines observed. In the case of benzene radical, the unpaired electron density is delocalized over 6 hydrogen atoms. Therefore, there are n plus 1 septet. There are 7 lines observed with the intensity ratio using Pascal diagram. It is obtained 1, 2, 3, 4, 5, 6, 7. Let us now see naphthalene anion radicals similar to benzene anion radical. Here there are two types of protons: alpha proton, 4 alpha protons and 4 beta protons. Therefore, they have different chemical shift as well as different coupling constant. For example, the coupling constant, hyperfine coupling constant A for alpha proton is 4.9 Gauss, A beta is 1.83 Gauss. The unit for hyperfine coupling constant is Gauss, whereas J in Hertz. The formula used to calculate the number of lines is 2Ni plus 1 into 2Ni2 plus 1. Therefore, 2 into N4 and proton I equal to 1 by 2. Therefore, there are 25 lines. It agrees with the number of lines obtained in the actual NMR spectra. Here, what is McConnell's relation? This gives the relationship between the hyperfine coupling constant and the unpaired spin electron density. If the unpaired electron spin density is larger, then the hyperfine coupling constant is larger. The unpaired electron couples with the proton. The hyperfine coupling constant is equal to Q rho C, where Q is an empirical constant, proportionality constant. It is for hydrocarbon radical 20 to 30 Gauss. Using this expression, once you know the hyperfine coupling constant from the experiment, Q value is known, you can calculate the unpaired electron density. Rho C will give the unpaired electron density distribution. Using this, we can predict the chemical reactivity site. Uh, Here we will study the EPR of DPPH radical. It is an EPR reference compound similar to TMS. Tetramethylsilane is the NMR reference compound. Diphenylpicryl hydroxyl radical is a reference for EPR. It is a field marker. It is a field marker. For example, this is the EPR spectra of exchange coupled copper complex. This is the DPPH signal. In the solid state, it occurs as a singlet. It exhibits a single line because of exchange narrowing due to Heisenberg spin exchange. DPPH, the solid state, gives a single line due to exchange coupling, exchange narrowing. Okay, let us see the structure of DPPH. The unpaired electron is delocalized over two nitrogen atoms. Therefore, I equal to 1 for nitrogen 14. There are two nitrogen atoms, 2Ni plus 1. There are 5 lines with the intensity ratio as obtained here. It is very, very important. And this question was asked in CSIR or GATE. DPH is a field marker. Using this, the G value for the since the G value for the DPPH is 2.0023, it is known. Therefore, the G value for the copper complex, iron complex, or any free radicals can be calculated using this as reference compound.